Can everyone hear me? Maybe? Yep. Yep. Okay, great. Okay, so I'm going to speak about agreeing on decisions. Really just, it's part of the agreeing to disagree literature. Maybe quite a few of you will be familiar with Aumann's agreeing to disagree result. So it says roughly that if agents have a common prior, then if their posteriors are obtained from updating over private information, if their posteriors rather are commonly known, then their posteriors must be the same. Bacharach extended this result to a non-probabilistic framework. So essentially, what happens is information is modeled as you have a set of states, and subsets of the state space are supposed to somehow represent information, and a decision function simply maps from these subsets of the state space into an action space, and in that way we're thinking of decisions as being functions of information. So what Bacharach did is that he has these decision functions over a state space, and he isolated the relevant properties that drive Aumann's result and imposed them as conditions over those decision functions in order to derive the same result in a non-probabilistic setting. So what he imposes is the sure thing principle over the decision functions. So it's roughly the intuition for this is to say something like, if you take the same action in every case when you're more informed, then you would take the same action in the case when you're more ignorant. The original intuition for this is found in Savage's book in probability, which is in single agent decision theory. And I think that's quite relevant because here we're looking at many agents we're looking at interactive information over a state space, and I think it's important that the sure thing principle was actually derived from single agent setting, and I'll come back to that later. The other condition is like-mindedness, which simply says that the agents have the same decision function. Moses and Nahum found conceptual flaws in Bacharach's setup. Essentially, the conditions that he imposes on the decision functions forces them to be defined over events or sets of states that are informationally meaningless in the model. I'll come back to exactly what this means later on. But as a result of this, of the problems that were pointed out here, there were several solutions that were sort of proposed in literature. Moses Nahum was one of them. Aumann and Hart have an unpublished paper on this, and Samet recently also had proposed something. And I'll come back to these and explain how what I've done relates to these papers. So in this paper, I have a new agreeing to disagree result. So the main argument essentially in the paper is that what's missing in Bacharach's framework is the machinery to be able to talk about counterfactual information. And essentially, implicitly, somehow Bacharach is forcing decisions to be defined over information that is supposed to, that is counterfactual. So what I do is I have a constructive method of expanding the usual model into one where you can capture this counterfactual information, and the decision functions are, among other things, defined over the information that agents have at the counterfactual states that I'll be adding in. And then I adapt the definitions of the sure thing principle and of like-mindedness within a new framework. What I show is that within this framework now, I can obviously prove a new agreeing to disagree result, but I also show that the decisions are only defined over events that are informationally meaningful now. Furthermore, the sure thing principle, I think, is more intuitive in the revised version that I have is more intuitive than the version that's found in Bacharach, and it's closer to the original intuition of Savage. And the new definition of like-mindedness is also similarly, I think, just a bit neater. So what I'll do here is I'll go through Bacharach's framework, show what the problems are in it. I develop the new framework and present the new result. Then I explain how the new framework resolves the conceptual flaws and give an interpretation to the sure thing principle. And then finally, I'll relate my paper to the other papers in the literature. So, okay, this is fairly standard now. We have a finite set of states, a set of agents, and this is how we're going to be thinking about modeling information. Any subset of states is called an event. And we just have a binary relation over the set of states. So, and this is a reachability relation. And an information structure is then this tuple, which consists of the set of states, the agents, and the reachability relations, one for each agent. Then this is all fairly standard. So a possibility set at state omega for any agent I is essentially we're thinking about epistemic possibility. So we're really thinking of something like these are all the states that I consider as possible from omega. And then from this we define the standard belief operators. So this is the belief operator. Here there's the mutual belief operator, which we can then iterate to get the common belief operator. So this is all fairly standard. I haven't imposed yet any conditions on the reachability relations, which is why I'm talking about belief. But really, I'll be restricting myself to very particular classes. In Baccarat, we're dealing with partitional information structures. So here we're thinking of the reachability relations rather as being equivalence relations, and they then partition the state space. So here's a state space, and then here we have two agents, blue and red. Here the partitions look like this, and here we're really thinking of say at this state the blue agent considers these 6 states, cannot distinguish between any of these 6 states, and this represents somehow the information that the agent has. Similarly for the red agent. Oh yes, sorry, yeah, okay. Okay, and so now we have this, so Baccarat defines an action function, which maps from the set of states into a set of actions. So essentially we'll just map with every state an action for every agent. And then we have a decision function, which now maps from essentially just subsets of the state space into actions, and then we impose some measurability condition, which essentially what we're saying is that for any states that you consider indistinguishable, whatever your decision is over them, the action must be the same in all of those states. And so what ends up happening here, for example, is that the blue agent, let's say, takes action X in each one of the states in this partition element, and this partition element. Similarly, the red agent takes action Y in those partition elements. At each state in those partition elements. The sure thing principle then says that for any set of disjoint events, if over every event in this set your decision is X, then over the union of each one of those events, your decision must also be X. So here again, the intuition is that if in every case where you have somehow the finer information, you take action X, then you'll take also action X in the case when you have the coarser information. So coming back to here we're looking at something like the union of these partition elements, and here we're taking action X at each state within this union. And similarly for the red agent, then the sure thing principle tells you that you'd be taking action X. Your decision function would require you to take action X over the set of states that corresponds to the union of all the partition elements. Note here that it's common knowledge at any of these states over here that I'm trying to outline. It's common knowledge that the blue agent is taking action X, and it's common knowledge that the red agent is taking action Y. Yeah, I hope that's clear. So the second condition that's imposed on the decision function is like-mindedness, which says that the agents have the same decision function. So what ends up happening here is, well, here action X is being taken over this subset of states. Here action Y is being taken over that subset of states, but they're the same subset of states, so by like-mindedness, the actions must be the same. So this is really somehow also just an outline of the Bacharach's proof. This is just a formal statement of the theorem. So if the decisions satisfy the Schrödinger principle and the agents are like-minded, then if it's common knowledge that their actions are whatever they are, then the actions must be the same. The problem is that the decisions are not always defined over primitives of the model. So, I'll make that clear in a moment. So here we can say that an event E is a possible belief for an agent I if there exists a state at which this event corresponds to a possibility set for the agent. The problem is that like-mindedness forces the decision of one agent to be defined over the partition elements of another agent. So, for example, here the blue agent has to have his decision function, obviously, decision mapping from these partition elements into an action space. But when we require the decision functions to be the same, then the blue agent's decision function must also map from these partition elements into an action space. But these partition elements are informationally meaningless for the blue agent because the blue agent never actually has this information. The other problem is that the Schrödinger principle forces decisions to be defined over unions of possibility sets, but no union of possibility sets is a possible belief for any agent. So here, the blue agent has his decision function mapping from this partition element, and this partition element. Their union is this. So by the Schrödinger principle, for the Schrödinger principle to be well defined, the decision function must map from this entire set of states into the action space. But it's not clear what the information is that's here because it's not a primitive of the model. We haven't actually. This is supposed to represent all the information that the blue agent has, so this is somehow outside of the model. The other problem that I'd point out is simply that, well, when we're talking about, let's suppose that somehow this represents being more ignorant for the blue agent. It's not clear what information the red agent has in that situation as well. Is it also the case, for example, that the red agent now knows that the blue agent has this information, or does the red agent still think that this is the model in which we're in, and where the partition element for the blue agent is still this one? So what I'll be doing now is to develop a framework in which I can interpret the information here as being the information that the blue agent has when the blue agent is secretly and counterfactually more ignorant. So what this means is that this will represent the blue agent becoming more ignorant, and I'll give a definition of that in a moment. And it's also secret in the sense that the red agent still will believe that the blue agent's information is given over here by this by the original partition element. So let's take a partitional structure. So this is what we'd usually be working with, the blue agent and the red agent. So what I'm suggesting is to add a set of counterfactual states to the model, and I'll be linking them in a particular way back to the original model. And at these states now, the information that will be here will be counterfactual information, and it will be represent being counterfactually more ignorant. So the trick is really in how these are linked up back into here. So I'm just going to introduce a bit of notation. Here we're talking about a partitional information structure. I'm going to simply let this be information cells, or just partition elements. This is the partition element that contains the state omega. And this is the actual partition over omega. And finally, I'm going to have the set gamma. Gamma is going to be all the partition elements for agent I and all the possible unions of those partition elements for agent I. And this will actually be the domain of my decision functions now. Here's an example. There are 3 states, 2 agents. Let's suppose that these are their partitions, and now the sets gamma are given like this. So I think that's fairly straightforward. Now we can create this new structure. We're going to be calling the new structure the counterfactual structure of S. So it's going to be the original set of states plus this new set of states that are going to be the counterfactual states. And the accessibility relations will be essentially the original relations plus new links from the counterfactual set of states back into the original ones. I still write this in the full model. I'm still talking about the possibility sets, and I denote them by B. For every agent and for every event in this set gamma, I'm going to create a new set of states. So for example, I know that this is going to be in gamma for agent A. Then I'm going to create this set of states where I simply duplicate every single state. So I have a duplicate for omega 0, a duplicate for omega 1, a duplicate for omega 2. But I'm indexing it by the agent A and by this event that's in the set gamma. So here, for example, I have the original model, and I've just added 3 states. But I do this, again, for every agent and for every event in the set gamma. So the full set of added states will consist of the union of all those states, all those sets of states. Sorry. Now I'm going to link the new set of states back into the old ones. So for example, let's add the ones from the set that I've just created into omega. So what I do is for agent A, if the state omega is in this set that we're interested in, then the counterfactual state will point back into every state that was in that's in the superscript. And otherwise, for every agent, the counterfactual state of say the counterfactual state of omega 2 is this state, and for this state will simply point back into the partition element of omega 2. So just to be clear, so this is for the other agent. So here the agent B had this partition element, and now at this state, the agent still thinks that that he's back into this information cell. And at this state, the agent thinks he's still back into this information cell. Just to do another example, suppose that now there's another set, which is omega, which belongs to gamma here. Then I can look at the set of states that I create. If I link them back, this time we're coarsening the information for agent A. So agent A now at this counterfactual state believes that he's anywhere in any of the 3 original states. For the red agent, nothing changes. So I have a formal definition of this in the paper, obviously, but this is just to give you an idea of how it works. So the reachability relations in the counterfactual structure now are serial intransitive, which basically means that I'm no longer satisfying the truth axiom or negative introspection. The reason why I do lose negative introspection here, in a richer framework, I don't necessarily have to lose it. So here I don't have a valuation function, so I'm not really dealing with a Kripke structure proper. But in a Kripke structure, I can it's possible to I think keep negative introspection without any problem. But we can discuss this after the talk. Anyway, so I have now this counterfactual information structure. Again, I have an action function that maps from now the full set of states into the actions. A decision function that maps now from the set gamma I, into set of actions, and again I have this measurability thing, which basically says that for any given states where you have the same information, you take the same action. Now, the sure thing principle says that for any subset of your original partition, if in every element of this subset you take the same action x, then if in every element you take the same action x, then you will take the same action over the union of these things. So here, one thing to note is that I'm requiring this jointness of the events. Because I'm picking out a subset from the partitions, from the partition of the state space, and so I'm talking about disjoint events. And the like-mindedness assumption requires that if there is an event that's the same in the domain of agents I and j, the domain of the decision function for I and j, then your decision will be the same. The decision of I over this event will be the same as the decision of j over this event. So this will be my like-mindedness assumption. And now I can, again, derive the agreeing to disagree result. So if now the decision functions satisfy this new version of a sure thing principle and agents are like-minded in the sense that I've just described, then if it's common knowledge that the actions of the agents are what they are, then their actions must be the same. But that's not really the punchline. It mostly comes here. So first of all, this deals with the conceptual flaws in the sense that now this gamma I, the domain of the decision function for every agent, is exactly the set of all possible beliefs for that agent, which means that the information is primitive in the model that I'm talking about. So so I'm always the decision is always defined over a set of states that's informationally meaningful. So now I don't have this problem where like-mindedness, say, requires the decision of one agent to be defined over a partition element of another agent. The other thing is that now we can give an interpretation to the sure thing principle. So this is the interpretation that I'd give it, which is that if the agent takes the same action in every case when she's more informed, she would take the same action if she were secretly more ignorant. What this means is this. Suppose we take this state here, which corresponds to this state here. So this is the partition of the red agent, of the blue agent. There will exist, and suppose that the event in the domain that we're interested in is for the blue agent, and we're considering the union of these three partition elements. Then there will exist a counterfactual state that corresponds precisely to the blue agent over this union of the blue agent's partition elements, which means that it will link back into every state in this union, and only back into this partition element of the red agent, which means that at this state, the blue agent thinks that the state could be any of the states in this union, so the blue agent has become more ignorant now, whereas the red agent still believes that we're back here. And this is back into the original model, so as far as the red agent is concerned, the blue agent's partition is still this one. So it's counterfactual in the sense that obviously the red agent now has false beliefs about, in a sense, about the blue agent's information, and obviously the blue agent has this belief that his information is actually, or rather, the blue agent's information is now this, but in the real model, if you like, it's still the original partition. And furthermore, it's secret because obviously the red agent doesn't realize that the blue agent has this information at this counterfactual state. Right. So here, this is just to state the fact that this represents ignorance more formally. So for any event in the original, for any two states in the original model, I will believe that E at the counterfactual state that corresponds to these two states if and only if I believes E at both those states, which means that if you somehow lose information at either one of those states or at both, then you no longer have then you've become more ignorant. Right, and so methodologically, so having an original model and then adding a set of states over and above it and somehow linking those states back into the original model is related to the impossible possible worlds modeling of Wanzing. And so essentially what I'm doing here is to use it in a particular way that allows me to talk about particular counterfactual situations that I'm interested in, which are obviously the ones in which you're somehow more ignorant. So as a solution to the problems raised by Moses and Nachum, Moses and Nachum's paper does provide conditions under which an information structure will give you the agreeing to disagree result without any problems. So essentially, they have a function which maps from the set of states to relevant information, and the decision functions are mapped from the relevant information into actions. But it's not constructive, so it's not always obvious right away to see whether the, I think anyway, whether the model that you're dealing with will give you the right, has the right properties. Aumann and Hart have a syntactic approach in which they also solve the problem, but they impose conditions on higher order beliefs. Essentially, they require the decision functions not to be independent of what happens at higher orders of information. I don't need to impose such a condition. And Samet in 2010 also has a version of an agreeing to disagree result in a non-probabilistic setting. The assumptions, the conditions that are imposed on the decision functions there are sort of quite different from what's in the literature. So he has an interpersonal Schrödinger principle, which essentially says that if I know that you have better information than me, and I know what action you're taking, then I'll just take the same action. So this at least requires two agents to be part of the. So the interpersonal Schrödinger principle is at least across two agents, but it's not clear to me what a single agent version of that would be, or if there is anything like that. So in a sense, the version of the Schrödinger principle that I'm giving here allows you to just have the same Schrödinger principle for both a single agent setting and a multiple agent setting. Essentially, just extend the single agent setting to multiple agent setting where somehow the information of all the other agents simply doesn't change. And in that sense, I think it's quite close to the original version by Savage. And that's it. Thank you.
Okay, so thanks. This is, as Yoram said, this is joint work with Jan Gankuli. And I'd like to proceed slowly with the motivation and explanation. Can we keep just the projector on, because I'd like to use the blackboard? Okay, great. Okay, it's getting better. Okay, so let's first remind how game theorists or economists deal with asymmetric information. So ever since Harsanyi introduced typespaces, okay, that's the machinery that economists are using. And what's a type space? Okay, so let's draw an example for the simpler case of two players. Okay, so we have a space of states of nature. Okay, S, and we have the types of player 1. Okay, and we have the types of player 2. So in this case, this would be a three-dimensional space. Okay, and if I'm a particular type of player 1, okay, if I'm player 1 and I have this type, okay, then I would know my type, but I wouldn't know necessarily what's the state of nature. I wouldn't know necessarily what the type of the other player is, okay. So I would have, right, so I would have something, okay, I would have a set like this that I would consider as possible, okay. And I would have some probability measure over this set. Okay, so you can think of it as a partitional crypto structure augmented with probabilities on each of the partition cells. Okay, this is as a first approximation. Okay, this is the approach. Okay, and what I've written here, okay, is that an important thing to. Okay, so what is this probability? Okay, here in TAC we are very much used to talk about knowledge and probability, and we feel very comfortable with it. Okay, so if I ask Yoram, say, you know, do you think it's going to rain tomorrow? And you'd say no. He'd say most probably no. Okay, so I would say, no, is the chance less than 20%? And he would say, suppose he'd say no. Okay, then if I were a hardcore economist, I would say, no, this is just cheap talk, okay? How can I know that, I mean, what does it mean that Yoram thinks that it's less than 20%? You know, the only thing that I can observe is what Yoram is doing, okay? Is he going to take an umbrella? Tomorrow this imposes some small inconvenience, but, you know, okay? So for economists, okay, these probabilities always come from preferences over acts. Okay, so what are preferences over acts? So in the simple example I just gave, there is just an issue of the state of nature. Okay, so let's take another example. Suppose the state of nature is, you know, different states specify, you know, either that there's no earthquake, or maybe there is a small earthquake or a larger earthquake, and so forth. Okay. So, and then you ask, you know, what happens to somebody's wealth, okay? So if there's no earthquake, the wealth is this, okay? But it declines the, you know, the harsher the earthquake is, okay? So there's one act for the agent in this case, which would be do nothing. If the agent does nothing, okay, this will be the outcome, okay? The outcome, of course, will depend on the state, okay? But maybe the agent is offered some insurance, okay, that will guarantee that the agent will have the same wealth no matter what happens, right? So this will be the insurance premium, basically, okay? But then the agent will be fully compensated. This is a full insurance no matter what happens, okay? And then the economist would say, you know, the only information that I have is whether the agent prefers this act over this act. This is the act of doing nothing, okay? And this is the act by insurance, okay? These are physical acts, okay, that the agent can choose between. And by observing, you know, hypothetically at least, you know, across all the choices among such acts that the agent can choose, then we can, you know, we can pin down the preferences. And under certain assumptions, okay, the axioms that Savage proposed, then, well, the conclusion would be, the agent has some probability measure over the space of states of nature. In this case, this would be the probabilities of different earthquakes of different magnitudes, okay, and the agent just compares the expected wealth, and according to this, the agent compares, okay, this would be one thing, you know, or there would be, this would be the case of risk neutrality, or we could, you know, have more complicated things, but the important thing is that under certain conditions, there would be some probability measure over the states that is very much related to the preferences, okay? In the case that there is also another player around, okay, in this case player 2, then of course the act in general, okay, may depend, the outcome may depend on also what the other agent is doing, right, or the other player. The other player may act in a benevolent way, in a malevolent way towards me if I'm player 1, okay. So there would be various outcomes depending on various acts that I can choose. And again, under certain conditions, okay, under certain conditions, my preferences would, you would be able to represent them as if I have a probability measure over the base space here, okay? Now, more and more economists look also into preference relations over acts, okay, that are not representable by expected utility with respect to some probability measure, okay? So, and these go and become more and more general, okay? And this is the issue that I'd like to address today, okay? This is, you know, becoming more and more popular. It's still on the margin of game theory, but still already becoming more and more popular, okay? And I'll give examples shortly, okay? So, the next question, okay, that intrigues economists is the issue of the existence. So this is a particular type space, okay? And the next question that intrigues economists is, you know, typically in applied examples, we use some small type space. Maybe I only have 17 types, you have 30, okay? Because, you know, for the particular problem that we're handling, this is enough, okay? For instance, suppose I compete with Burkhardt over a license for drilling oil somewhere, okay? I do a test drill and I know the outcome. I know that Burkhardt also did a test drill. I know that according to the state-of-the-art science in geology, then the tests are correlated, will be correlated in a very particular way, okay? But it's also also common knowledge among us that we have access to the state-of-the-art science, okay? So in this sense, higher order beliefs would be trivial. I mean, I would have some uncertainty about the test results of Burkhardt, okay, but I know that conditional on each test result, what he believes about me, okay, is according to science, and he knows that I believe that he believes about me according to state-of-the-art science and so forth, okay? So this is a very particular case of higher order beliefs that are trivial. So whenever we do the strategic analysis, we ask ourselves, is it the case that the fact that we looked at a very particular type space, okay, where we excluded interesting or complicated higher order beliefs, does this change in any way the outcome of the strategic analysis if we compute Nash equilibrium or Bayesian Nash equilibrium or rationalizable strategies or whatever solution concept that we're interested in? You know, does it make a difference, okay? So the question then becomes, suppose we were also to look at potential higher order beliefs that are more complicated and embed this small type space in a universal type space, okay? Would this change the analysis, okay? And for some solution concepts, at least the answer is no, okay? If I take a small type space and embed it in a larger type space, if I find an equilibrium for the larger type space, then it induces also an equilibrium for the smaller type space that is embedded inside, okay? So, so this begs the question, does there exist such a universal space into which I could potentially embed every other type space, okay? So that's the question of existence of a universal space. And for the classical case of probabilistic beliefs, where beliefs are represented by probabilistic beliefs, we know that the answer is yes, okay? And this has been done in two different ways. Under one approach, you need some topological assumptions about the space of states of nature S, okay? And then, you can show, so this was pioneered by Mertens and Zamir, and then others followed suit with other topological assumptions, okay? And there is also an alternative approach which does everything in a measurable theoretic way, okay? And there, the method of proof is different, but there again, a paper by Dov Samet and myself from '98 shows that also without topological assumptions, a universal space and universal type space exists. Okay, so what we would like to explore in this work is, okay, the same question, but the case of more general preferences. If I have some more weird preferences that cannot be represented by a probability measure here, okay, would it still be the case that the type, there would be a universal type space, okay? So that's the, or under what conditions would we know that there exists a universal type space? So that's the question that we are addressing here, okay? So there is some prior work on this. First, there's a work by Di Tiglio, okay, who showed that, okay, so if you think about it, why are these type spaces enough actually to represent what we need? Okay, this is something that we know very well from logic. Okay, so this type has a belief about nature and the other player's types. Okay, but in particular, it induces marginal beliefs on nature. Okay, the same for the other player. For every type of the other player, the beliefs of the other player that would be somewhere here would induce some beliefs over, would induce some marginal beliefs over S, okay? So this allows us to unfold the beliefs inductively, right? I mean, I have some beliefs about nature, but I also have but then I can also find out my beliefs about nature and the other players' first order beliefs about nature. And then I can find out my beliefs about nature and the other players' first order belief and second order beliefs about nature, and so on. Okay? So the question is essentially, when I have such an infinite hierarchy of beliefs, okay, in some sense, does it pin down, okay, a limit belief? Okay, this is the case for probabilistic beliefs. So what Alfredo Di Tiglio showed that if for some reason, okay, the set of events that I'm interested in is an algebra of events, it's not a sigma algebra of events, then very mild conditions will do, okay? And essentially the intuition is that, when I go to the limit, I don't add in the limit any more events that I haven't considered this far, okay? So this is one approach, okay? But if I am interested in sigma algebras, then there is work by Epstein and Wang, and also Yichun Chen, okay, that showed some topological conditions under which, that when they are satisfied, some regularity conditions, a universal space exists also for general sets when types have preferences, okay, that cannot necessarily be represented by beliefs or probabilistic beliefs, as long as some regularity conditions obtain.
Still need the light?
Yes. So, okay. So let's give up the light, the projectors, and okay. So the result I'd like to present here today is that actually, by following the measure theoretic approach that I started with Dov Summit in '98, okay, we can show actually that a universal space exists for, a large class of preferences, as long as they can be represented by a countable collection of continuous functionals over X, even if the preferences themselves are discontinuous. Okay, and I want to proceed, with one main or important example here is the case of lexicographic preferences. So what are lexicographic preferences in the most, in the simplest case? Suppose I'm very egoistic, so I always prefer to have one more rupee to less, okay? And I don't care about that as a result of this, Burkhardt loses $1,000. But, once I have this, if you give me two options that under which I have the same amount of money, then I'm happier that Burkhardt has $1,000 more, okay? So this this means that I look at things lexicographically, right? I first look at my own wealth, and only next I look. So I'm extremely egoistic. This is a preference relation which is discontinuous, okay? Because you know there could be a sequence of outcomes by which I compare pairs of outcomes by which Burkhardt has. I always prefer to have, 10 rupees more, 9 rupees more, 8 rupees more, okay? As long as Burkhardt, even if Burkhardt has $1,000 less, okay? But suddenly in the limit, when I have the same amount of money, okay, I want to reverse the order. I do want Burkhardt to have $1,000 more, okay? So the preferences themselves are discontinuous, but there are, I can still represent them with two functionals, okay? With my first order preference, which regard myself, and then the second order preference that look at Burkhardt's wealth, okay? So I want to proceed by, talking about, I'm not going to show any details, but I just want to talk about the intuition of how the theorem works for this specific case of lexicographic beliefs, okay? Hoping that this will, give some intuition. And as I said, we are generalizing the approach from Hefetz and Samet 98. Okay, a key technical point here would be using a monotone functional class theorem, okay? That would, okay, so maybe let's put it as follows. The general strategy of constructing the universal space would be to say, I have this type space, and I have that type space, and I have this type space. I have a large category of type spaces, okay? In each type space, each type is associated not with a probability measure, but with a preference relation over X, okay? Now, whenever and as we said, in each type, okay, each type in particular introduces a preference over X that depend only on the state of nature. Preferences over X that depend on states of nature and the other players' first-order preferences, okay? On nature, first-order preferences and second-order preferences and so forth. So I have a hierarchy of preference relations, okay? So I collect all the hierarchies that appear for me in some type space, okay? I just collect them in one big pool, okay? And I use the preference that, so if I took a hierarchy from some type space, I just use the preference relation that comes from that hierarchy. Okay, what I want to show is that, this pool of hierarchies, okay, actually forms a type space, and this will be this universal type space, okay? So essentially there are two things, okay, if I have to hold in order for this pool of hierarchies to be a type space, okay? One thing, okay, is the fact that, I have this hierarchy of preferences. It must be the case that this pins down a unique limit preference, okay? Now, in the classical case of Mertens and Zamir of probabilistic belief, just the fact that I have sigma additive probabilities, this just induces the right kind of continuity, okay? In the case of lexicographic beliefs, I will not have the continuity of preferences, but I have in this example, two functionals. Each of them is continuous, okay? So I will know what the limit functional is, okay? And so I will know what the limit preferences are, even though, again, the preference relation itself is discontinuous. So pinning down what happens in the limit is one important feature, okay? And the second thing that has to happen, okay, is that when I move from one to belief, in our case to preferences, has to change in a measurable way, okay? And that's the point where we're using a functional monotone class theorem to guarantee this measurability, okay? So these are the two key insights that we're using. And I will show some details in the time left, okay? But it's just to give an idea. Yes? I'm sorry?
Continuity here is preserving limits.
Continuity here is pinning down, okay, what the limit preference, okay? So for instance, just if you want a case where this doesn't happen, is suppose that take a classical case of probabilities, but probabilities that are only finitely additive. Okay, so you can easily, construct an example where you have, a hierarchy of beliefs. Each of them has actually a finite domain, so they, they're well defined. Okay, but this hierarchy of beliefs will not define. If you only assume finite additivity, if you take any tail event, non-trivial tail event, it will not pin down what the probability of the tail event will be, okay? So only if you assume sigma additivity, then it pins down the probability of the tail event, okay? So there is no universal space for finitely additive types that are finitely additive beliefs, okay? But in this case, okay, there will be, okay? So that's the point. Okay, so... Okay, so I will just sketch, something for the proof of the particular case of lexicographic preferences. Okay, so as I said, what we do here is we look at acts, okay, that are real valued, measurable, and bounded from, whatever space we have to the real line. Okay, then a two-level lexicographic preference is represented by two functionals, okay, over acts. Okay. Such that if I weakly prefer f over g, then, u of f is, is larger in this particular order relation from u of g. U is a pair of numbers. U of f is a pair of numbers. U of g is a pair of numbers. Okay, so when is a pair of number lexicographically larger or greater than the other, if the first is strictly larger than the second, or if they are the same, then the second has to be at least as large, right? So, okay. Now, a particular case of this would be that these functionals are linear, okay, but I do not even have to assume this even for the sake of the example. Okay, if they are linear, then the Ritz representation theorem, they can be represented by a pair of probability measures, okay, but you can forget about this. Okay, so what are the basic events that we're looking at? Okay, so this will be the event that the functional L assigns to f, okay, a larger number than RL, okay, and this will be the reverse, larger or equal, and this will be the reverse case, okay. So these are basic events talking about, any analysis that you might like to do, okay, will have to look into such basic events, at least those, okay? And the actual interesting events are really those, okay? So what is the event that, for instance, F is preferred to F is some act, okay, you can think of R. Okay, you can think of R as if you like, a constant act. Okay, what is the set of preference relations that prefer F over R? You would like this to be a measurable event. Okay, you would like to be able to talk, and the second one is just the reverse. Okay, so these are the basic events, and the important thing is to know that if these are measurable, if these events are measurable, then also these are measurable because if I have so the preference relation is what? What is the set of pairs of numbers? So if I have R1 here and R2 here, okay, what is the set of pairs of numbers that are preferred to this? Okay, it's this, right? This is not, okay, and then all, okay. Okay, so these are all sets of numbers, including this part, okay, but not including this, that are preferred to this pair of numbers. Okay, so we see this is not a closed set, okay, and this is why the preference relation is discontinuous, but it is a Borel set, okay, it is easily expressed, I mean, as is written here, you know, by conjunction, disjunction, I mean, complements and so forth of the basic events. Okay? And so what's a type space? What's a type space? Then, you know, as I said, this, you know, we have a state of nature, and we have, for each player, we have a mapping from types to preferences over the nature and the other player's types. Okay, this is formally what it is. Okay, and this type, as I said, it induces a hierarchy of beliefs over nature, over X that depend only on nature, over X that depend on nature and the other player first order preferences and so forth. Okay. Now, what is a type morphism? Now, I want to talk about embedding a type space into another bigger type space. Okay, I will not write down the formal definition because I don't have the time. But again, it will be something that preserves the state of nature and the preferences. So this is the. So it's not difficult to show that type morphisms preserve the hierarchies I was talking about. Okay. A universal type space is, by definition, okay, this is a terminal object in the category of type spaces with these morphisms. So it's a type space which admits a unique type morphism from each other type spaces into it. Okay? So again, in some sense, I already told you the idea of the proof. We pull together all the hierarchies that appear in some type spaces, okay? And we attach to this type, to each such hierarchy, the lexicographic preference that appear in the type space from which it came. Then, as I said, we use a monotone functional class theorem to show that this mapping is measurable. Okay, and this essentially, you know, these were the two. These were the two crucial points in the proof. Okay, all the rest is, you know, follows known footsteps. Okay. So yeah, that's what I had to tell you.